All right, hello again. My name is John Petsy with Sky Foundry. I'm a partner, co-founder in the company. We make analytics software for the built environment. And today's topic is about the move of analytics to the edge. And we want to talk about the role of edge computing in analytics and energy management in built environment applications. And we'll talk about what the edge means, the cloud, distributed computing architectures, clustering, replication. We want to describe what we mean by these terms and why they're important. So let's start here. First of all, analytics. What we mean by analytics is creating value from device, equipment, and sensor data. And the primary way that's done is software that automatically detects patterns that represent deviations, anomalies, faults, opportunities for savings, all types of information that we can glean from the data from our equipment systems. And analytics has become well proven. Our own company, we see our software deployed to well over 1 billion square feet worldwide, delivering financial value to owners and operators. The result with analytics is you know what your systems are really doing. An analytics software platform automatically processes analytic rules and algorithms on the data coming from your equipment systems, whether that's live data or batch data. And it detects patterns, relationships, correlations, trends, and then it automatically generates views to show you what's been found. So you see exactly how your systems really are performing, not what you might have hoped or believed. And here's some examples of the screens that the software automatically generates to show operators patterns of behavior in their systems, whether it's outright faults or trends or deviations. An interesting thing about analytics is it becomes an ever-present expert watching the performance of your systems. Rules get established, issues are detected, issues are corrected. If they ever come back again, the rules are sitting there waiting and looking at the data to find those issues. So the benefits of analytics are to identify equipment faults and then drive the workflow process to correct those issues, generate savings, improve comfort, identify predictive trends. Now this is very important. The ability to look at data and see loss of efficiency, increased energy consumption, other anomaly patterns that are actually predictive of faults or failures that might have a significant impact on your occupant comfort or your energy performance, etc. Another side of analytics is to automatically calculate and track key performance indicators, whether they're around energy consumption against baselines or goals or other requirements, whether they're around comfort metrics or sustainability metrics. The software automatically calculates the KPIs, charts them, graphs them, does the things that typically were done manually in the past. Importantly, analytics software is used to analyze environmental conditions to ensure that occupant comfort and safety levels are being achieved. Such things as number of air exchanges per hour, CO2 levels, VOC levels, and other things that affect the occupant experience. Analytics also identifies changes needed in control strategies. Identifying the building start too early, run too late is a simple but effective example. Analytics are the foundation for monitoring-based commissioning, continuous analysis and commissioning of systems. Instead of simply coming in and doing a commissioning, retro-commissioning project once a year, once every 5 years, analytics makes it a continuous, ongoing process detecting loss of performance, loss of efficiency. And finally, a key benefit of analytics is it gives you the information to better evaluate and justify your expenditures, both capital expenses to replace equipment to be able to better justify those expenses, and operating costs. So we've talked about analytics. Now let's talk about analytics at the edge and this important need to address the whole edge to cloud data and compute requirements in the built environment. I want to start out with this quote from Harbor Research, one of the leading research firms in the Internet of Things industry environment, which of course smart buildings are part of. The IoT is a distributed computing challenge, and it starts with this key point. The reality is that it is not possible, it's not cost effective, and it's not even desirable to try to transmit every single piece of data from every single IoT device, every single sensor, up to a cloud before we can get value from it. And a good analogy is a self-driving car. Right? We can't wait for data to go to a cloud to make a decision for the self-driving car to put the brakes on so that we don't have an accident. That has to happen where? At the edge. And that's a good example of what we mean by the edge. Now, there's other things that happen very well at the cloud and, in fact, can only be accomplished at the cloud. Think about tracking the movement of all the cell phones and detecting that all of these cell phones that had been moving along at 60 miles an hour now are stopped. What have we detected? We've detected a traffic jam. That requires the aggregation of all that data at the cloud. So another way to look at this is, as powerful as cloud technologies are, the cloud is not a solution to everything that we need to do to operate our buildings and run them efficiently. So let's talk about some of the key terms here involved in analytics at the edge. First term, distributed architecture. What we mean by that is deploying a software application across multiple computing devices, multiple nodes, which distributes the work. Now, that work includes data collection, communicating with external systems, storing that data, analytics processing, control, making decisions for optimized control, and finally, presentation of data and findings to the user. So we want to distribute that across multiple computing nodes. The edge typically refers to those applications that are running on computing devices that are mounted on or close to the actual equipment system. So it might be a controller type device in an equipment room. It might be an embedded controller running on a piece of equipment. Those are all examples of the edge versus the cloud. And by the cloud, we mean applications that are running on computers and servers that are accessed over the internet and typically provided as a service offered by IT companies such as Amazon, Microsoft, IBM, Google, and others. Well, there's some other terms we need to describe here as well. If we're talking about distributing computing on multiple nodes, then we enter into the need to discuss clustering. And what we mean by clustering is connecting those distributed nodes into a unified system, so that users who interact with their data, their analytic results or reports, and their views, they interacted with it as if it was a single computer with a single database. So we take that distributed computing system, but for the end user, it becomes a seamless user experience, even though the data and processing are distributed across many computing nodes. And another point that we need to deal with, if we're going to distribute computing, data acquisition, analytics processing across multiple nodes, then we need to deal with how we're going to address potential downtime, failures, other issues with those nodes. And that brings us to the term of replication. And this is a feature that enables us to replicate fully operational copies of the application that's running in a distributed node. We can replicate that to other servers to provide redundancy and backup so that users can interact with their data even if the original data source, the original system, is offline. Now, of course, if the original system's offline, that replica is working with the last available data. All right, so that's the what. Key terms related to distributed computing and analytics at the edge. Now, let's talk about why this matters. We'll start with a brief view of a distributed architecture example. So here we can see that we have nodes of the application, in our case, our SkyFoundry SkySpark software, running at the cloud. And you see multiple nodes because what this allows is that you can instantiate multiple servers to scale to huge system sizes. And those dotted lines indicate that they're connected in a cluster so that they are forming a unified system. But now let's move down into the building. Here we're seeing the analytics software being installed on-premise. Key point, it's inside the secure network, the secure firewalls of that building, that organization, where you'll notice it's connected to the end devices. It acts as a security boundary for devices and equipment that may operate on protocols that don't have the security levels needed to go over the internet. But we can take that to the next step, where we see the analytics software actually deployed on embedded devices that are actually mounted on equipment systems. And again, as we distribute all these dotted lines indicate that all of this is being unified with a clustering technology so that the operator has a unified view. The operator doesn't have to worry about what node am I connecting to, right? They see their data from all their different systems, sensors, and equipment in a unified view. All right, so why does it matter? Well, there's a number of very compelling reasons that analytics and other data-related applications are moving to the edge. The first one is greater fault tolerance. By having the process running out at the edge, we have greater fault tolerance for data collection, for data storage, for data processing. So we're collecting the data closer to its source, even on its source. We're processing the analytics and even creating the visualizations for users as close to the source as possible. And what this allows is in-building personnel to have full access to their data and analytic results, even if they can't communicate externally to the cloud. Think about an operator who's working in a major central plant, and a piece of equipment is making noise, sounding like it might be an impending failure. Imagine if they have to be able to connect out over the public internet to get to a cloud to see the data from the piece of equipment they're standing beside. That's not viable for most applications. Well, if we're running the application at the edge, that local operator has direct local access to all of the data, analytic results, control parameters, etc. Another reason, latency, the time it takes for data to go from one location to another. Well, increasingly, we want to provide more real-time data acquisition, processing of analytic rules, and automated control response, more intelligent control. Well, in order to do that, latency is an issue. So we want to be able to run the analytic process right there on board equipment systems without having to transmit that data up to the cloud. There's another latency issue, and that's what we call supporting applications with what are called constrained networks. They're limited in one way or another. IoT devices are often connected to slower bandwidth networks, or cellular networks, or other networks that have intermittent communication capabilities, or have high data transfer costs. Well, if we collect the data locally, we process the analytics, the only thing that goes up to the cloud, to the external user, is the final result. And you can see network traffic reduced by as much as 1,000 to 1 by keeping the data at the edge, processing the analytics at the edge, and only sending the results out. Another important reason is security, right? Keeping data on-premise may meet requirements for projects in mission-critical applications that simply can't send their data to an external cloud. We also mentioned that it can isolate in-building systems from the internet. There are many devices, control systems, and sensors that don't have high levels of security on their communication technology. And another example is meeting regulatory requirements that specifically say the data must stay here. It can't leave this state. It can't leave this country. Other reasons get to cost and simplicity. We can save engineering costs. If we're applying the same application environment at the edge and the cloud, that means you engineer the system once with one uniform set of tools, as opposed to previous concepts of different data collectors at the edge, different technology at the cloud. And by running it at the edge, we can eliminate hardware costs for gateways and other security appliances in many applications, not all, but many. And then providing that seamless user experience, right? The need to distribute computing, data collection, analytics processing is driven by the reality of the application, the buildings, network limitations, etc. But operators don't want to be bothered with that. They need to work with their data, their analytic results, their reports, their KPIs, as if it was a single system. Well, a distributed architecture provides for that. And then finally, that need for replication. A way to create a fully operational replica of every distributed node, loading it on another computer, maybe in the cloud, maybe some in the building, so the users have full access to all their data. Their queries don't even have to penetrate down to the actual nodes. This is often used in applications with constrained networks. Let me offer a perspective on this, because while we're talking about applying edge-to-cloud technology in the built environment, Think about it for a second. We actually live in a distributed computing world. If you bring up your browser, whether on your PC or your phone or your tablet, right, and do a search, find something you want, find a restaurant for this evening, right? You get it on that single pane of glass, but do you think about how that happened? Did all of that data, all that information get uploaded to your phone or tablet ahead of time? Was it all aggregated there? No, of course it wasn't. Did all of that information get aggregated to one single server someplace in the cloud? Did somebody previously have to assemble it all and store it in one place in case you were going to search for a restaurant tonight? Obviously, the answer is no. That is not how things work. You request what you want when you want it. That search goes out over a fabric of distributed nodes. It isn't aggregated in one place. And the reason for that is you can't do that. Then there's no need to do that. The web is a distributed computing environment. Well, we bring up the question, then why do people think that the only way to apply analytics and other data-oriented applications to the built environment is that we're going to have to bring every piece of data from hundreds, thousands, millions, or even billions of devices up to a single server first before we can analyze it, visualize it, present it, and gain value from it? And we see that there are a few reasons for this. One is that's the way it seems to have been done, right? And part of that is because the impact the cloud has made on changes of society's thinking about computing, right? And kind of an overfocus and maybe a belief that, well, the cloud's a solution to everything. Well, it's not a solution to the issues we've mentioned, which is latency, security, keeping data on-premise, providing local access for operators. And that leads to, have you made a complete assessment of the risks, the costs associated with communicating every piece of data to the cloud? I go back to our self-driving car application, right? We know that process of determining when to put the brakes on has to happen at the edge. And so SkyFoundry's addressed this challenge with technology we call SkySpark Everywhere. It's a true distributed computing edge-to-cloud platform for data collection and data analytics. And what it does is it brings truly advanced analytics to every level of the system to meet the different needs of what you need to do at the edge, at the middle layer, and at the cloud. So let's go back to our diagram here and look at it again with the perspective of the comments we've just reviewed. We have our cloud-based nodes. Multiple of them allows us to scale to huge system sizes, but we also have the ability to deploy the technology on-premise inside the secure firewall, keeping all the data on-premise. And we have the ability to bring it all the way down to embedded devices running on the equipment for near real-time operation, data collection, decision-making, optimized control. And then let's overlay on that replicas. We can replicate each one of these nodes at whatever frequency our application requires. We can replicate it in building. We can replicate it at the cloud, providing that backup of fully operational replicas with the last available data, giving users a high level of redundancy as network connections go down. Hopefully this presentation is going smooth today, but I'm sure over the last year we've all been involved in presentations where we had network interruptions, we had communication issues. Maybe we were able to get back on. We said our apologies. We continued on with our discussion or presentation, but think about the impact of that when we're talking control, automation, energy applications, comfort and safety issues. So what we've deployed and brought to the market is SkySpark Everywhere distributed architecture, providing true computing at the edge for data acquisition at the edge, communications, data storage, analytics processing, and visualization. And yet it can be connected into a fabric that provides unified, seamless views for our operators. So the result? Seamless data environment, even as applications span diverse equipment coming from different manufacturers, data coming in over different protocols, data coming in over different formats. And this is important because today the data produced by equipment systems is even more valuable than the equipment itself. It's an interesting point. Think about it, right? Think about a piece of equipment. How much money do you spend for it? That sounds like a lot of money, but what if you operate it improperly for a year? Most likely that'll cost more money than the equipment itself. So only by effectively bringing together data from these diverse devices in a unified and normalized platform can we get the value of that data. And as we've seen, in order to do that in the real world of the built environment, we need a distributed computing environment. It gives us a solution we need to provide for edge-based processes and cloud-based delivery of information to different users. So with that, I thank you for your time. That's a view of analytics moving to the edge, the what and the why. Thanks for your time.